So I hope the microphone is okay. 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 So as Shiraz explained to us, I'll be talking about some works that many people, including myself, have done recently, trying to understand the thermodynamic aspects, statistical aspects of supersymmetric black holes in AdS space-time. And as already Shiraz mentioned, that I first came to India 13 years ago, tried to better understand this question, discussing with Shiraz. This question was always a pain in my neck for more than 10 years. I hope I got some important clues about solving this problem. I won't claim that I solved it. So probably we can try to understand better this question. Okay. So I'm supposed to give 3 lectures. So today I'll try to explain some salient, the basic aspects of AdS black holes because it's an introduction, and the gauge theory aspects of it. And for quantitative studies, I'll try to explain to you the supersymmetric AdS5 black holes and how we can try to microscopically understand them. Especially today, I'll try to develop a higher dimensional version of Cardi formula. You know, the Cardi formula of 2-dimensional conformal field theory, in a sense, can be extended to higher dimensional CFTs in radial quantization. And I'll try to use that to microscopically better understand antidistant supersymmetric black holes in the large black hole limit, when some angular momentum is large and so on. Tomorrow, next lecture, I'll try to go beyond the large black hole limit and give some evidences that much more complicated or rich physics has to happen, even in this BPS sector of AdS 5 times S5, beyond the analytic black hole solution that we know. Okay? So I'll try to discuss some deconfinement transitions and find some evidences that there should exist new black hole-like large and saddle points beyond the solutions that we know. In the last lecture, I'll try to explain, divert a little bit. I'll try to explain to you more abstract anomaly-based methods of even-dimensional CFT, trying to have a better understanding on odd-dimensional AdS black holes. And if time permits, I'll try to discuss some studies we are doing on odd-dimensional CFTs, trying to understand even-dimensional AdS black holes in various dimensions, and shed more light on exotic deconfinement-like behavior, at least hint of them. Okay. So, well, it's a very basic introduction. I'll brief. So many people have been fascinated by these analogous thermodynamic properties carried by classical black hole solutions, where the area of black hole event horizon is given the role of entropies, and the surface gravity at the event horizon is given the role of temperature. Especially it's made more precise and more profound by the works of Bekenstein and Hawking, especially the Hawking radiation. And it's really a striking emergent behavior, trying to encode the black hole's quantum and thermal physics onto its geometry. So it has been providing great inspirations for many people trying to have creative and wild ideas, trying to better understand quantum gravity itself. Today's purpose, the main purpose of my lecture is a bit more conservative, and actually it's much more modest problem. It's trying to better establish the statistical interpretation of these black hole thermodynamics, appearing surprisingly as its geometry. Okay? So this kind of endeavor has been made from long ago, more than 2 decades ago. And the basic idea is to engineer the black hole systems from microscopic quantum field theory or quantum mechanics. So a nice method of doing so after the discovery of D-branes is to try to engineer black holes from D-branes, suitably wrapped and so on, so you get the same quantum numbers of these black holes. On D-branes, we know many microscopic descriptions, quantum field theory, gauge theories, and so on. So we can hope to use that to establish these thermodynamic behaviors in a statistical manner. Okay? The thing is that the reliability of these gravitational and geometric descriptions often demand us to study the strong coupling regimes of quantum mechanics or quantum field theories. So in general grounds, quantitative studies are quite difficult. So, so even more modest trial that people have made was to try to study some supersymmetric black holes in some supersymmetric compactifications of string theory, so that if you compute and study suitably chosen observables, they are protected against the change of continuous coupling constants of the theory, so that you can do a weak coupled calculus but still have some insight into the strong coupling regime. So that kind of study has been done more than 2 decades ago. And probably one of the quantitative successes I should mention is the one by Strominger and Waffer more than 2 decades ago, which studied specific supersymmetric BPS black holes And the technical idea which has been useful there, and for many other black hole studies later on, is to engineer certain D-brane systems and suitably compactify to get a temporary strings, so D1, D5 strings, compactifying D5s on certain 4 manifolds. And using some Cardi formula for this 2-dimensional quantum field theory engineered, one could understand some thermodynamic aspects, especially the entropy, in a very concise manner. So consider the 2-dimensional CFT compactified on a circle, and consider its partition function or index or whatever, whose chemical potential is conjugate to its momentum. Okay? So at large momentum limit or the small chemical potential limit, the asymptotic behavior of this partition function is given in the following way. Central charge divided by this chemical potential, so we call it Cardi behavior. Using these universal behaviors, doing simple Legendre transformation, one could get the Cardi formula for this entropy, which successfully explains the black Bekenstein-Hawking entropy given by its geometry. And many other successes have been made of this kind. But if you consider more complicated black holes examples, say in a given system, there turned out to be more and more complicated black holes, which are getting more and more harder to understand using these simple frameworks. So for instance, the example I explained to you, it's a single-centered black hole, but let's say in 4 and 5 dimensions, various settings, there turns out to be much more complicated black holes, multi-centered ones, black rings, and even some complicated geometries containing some hair-like configurations, sometimes superposed with black holes and so on. And it's not really easy to study all of them, as far as I can understand, in a unified settings. Okay? And some black holes even turned out to be a dominant large charge saddle points in non-Cardi regime, so you can't really use these simple kind of formulations. And often it turns out that even in a given system, to study different black holes, one uses different descriptions, sometimes ad hoc or sometimes different effective descriptions to understand aspects of different black holes. It's quite okay, but it might be more desirable if one can understand a single description to understand all sorts of different black holes in a uniform manner. So the subject of today's talk, and tomorrow's talk maybe, will be first to provide the uniform descriptions of many black hole-like saddle points in a given system using single description. And naturally, one is led to consider the anti-de Sitter black holes using the boundary conformal field theory using AdS CFT. So this will be motivating me to understand better the anti-de Sitter black holes from CFT. And secondly, it's a technical benefit. I'll try to establish a version of Cardi formula applicable for the indices of superconformal field theories in space-time dimension higher than 2. So I'll be presenting an analog of this kind of Cardi behavior for higher dimensional conformal field theories indices defined on sphere times temporal line. Okay? So these are 2 main subjects that I have in mind.
You are defining the Cardi limit to be P only about some large value of P. You are not writing it as P much greater than Q1, Q5 much greater than 1. It's just P, large P. You don't have to have large central charge.
But Cardi formula is valid for finite central charge and large momentum, right?
So I'm just okay. So because you need this long string thing.
Oh yeah.
In which you go to the continuum limit.
Yeah. In
which the level spacing becomes very small.
Yeah.
All that physics is not needed in this.
Here in 2-dimensional.
I think Gautam saying that in general the Cardi formula will only work for P much larger than some scale that scales with some positive power of C. So if C is order 1, P much larger than 1 is okay. If C is also large, P might have to be larger than 1.
Yeah.
Is that what you're saying?
That's the kind of
Yes. So in a sense, I'm just always discussing Cardi formula here and also later on for higher dimensional case as such suitably double scaling limit. So for instance, this will be replaced by n square, and this will be for my Cardi limit stuff to be applicable in a simplified manner. Probably I'll be taking my charges or angular momentum to be much larger than n square as well. I think that's the safest regime in which one can trust this Cardi formula, even in higher dimension. But some kinds of calculation I do in this safe regime turns out to be just valid for describing black holes away from this limit. For instance, this black hole entropy, some observabilized entropy formula, even if you go beyond this Cardi limit, it just turns out to be valid. but I don't have very good technical controls of it. All I observe is that, yeah. All I observe is that I do some double scaling limit of Cardi formula in higher dimensional CFT, and I observe that some computed observables continue to be valid beyond this Cardi regime. So yeah, but strictly speaking, here I'm referring to order 1 central charge and just large momentum, just more naively, yeah. But it turns out to be that formulae developed in that manner seems to be more applicable to in a more wider sense. But yeah. So anyway, I'm going to study the black holes in antidistant space higher than AdS4, higher than AdS3, and I'll be restricting my interest to technically controllable supersymmetric black holes soon. But let me just briefly motivate the physics by considering the simplest black holes in AdS space-time, namely the Schwarzschild black holes. Let's just stick to AdS5 for now. So AdS Schwarzschild black holes is a black holes embedded in global AdS3, having a 3-sphere as its spatial part of conformal boundary. And it's a spherically symmetric solution which has unsquashed S3 as a horizon as well. So if you consider this temperature and mass of this black hole and plot the relation, it takes the following form when multiplied by the radius of AdS5. Okay? So beyond critical temperature, it has 2 branches, one being small black hole, one being large black hole. Obviously, the size is small and large. And it turns out that the small black hole branch has negative specific heat. So it will be unstable in the canonical ensemble. And during my talk, this branch will be playing no important roles because I'll always restrict myself to canonical or the grand canonical ensemble. The large black hole branch has positive specific heat, and it plays a very important role in understanding AdS thermodynamics. Namely, it plays a very important role in understanding what's called the Hawking-Page phase transition, which is happening by a competition of 2 large-n saddle points. The first saddle point appearing in this competition is the large AdS black holes I mentioned. The second saddle point, which will be competing with it, is the thermal gas of gravitons in AdS. It has the characteristics that the small fluctuations of gravitons in AdS doesn't really see the inverse of Newton constant, or in gauge theory language n square. So it has a characteristic that its free energy scales like 0 power of n. The large black hole saddle point has its free energy being proportional to the inverse of this Newton constant, so the free energy is naturally proportional to n square. So if you let these two saddle points to compete, at lower temperature, the gas of graviton phase dominates, and it turns out that at high temperature, the free energy of black hole becomes negative, so it becomes dominant saddle point. Okay? So in between, there turns out to be a first-order phase transition called the Hawking-Page transition, beyond which temperature AdS black holes turns out to win over the gravitons. And this is still a review, basic review. And after the AdS CFT, the conformal field theory dual of this Hawking-Page transition has been naturally suggested to be the confinement-deconfinement transition, where at low temperature, the free energy of the field theory is also supposed to be 0th power in n. So it's naturally seeing not the full component of matrix degrees of freedom, but some gauge invariant combinations of them. In the deconfined phase, where free energy is supposed to scale like n squared, one sort of see the liberated degrees of freedom, each matrix elements of gluons and so on. And that has been studied in much more detail and concretely in 2003 by Aharoni, Masano, Shiraz, Papadodimios, and Ramsdorf, by studying the thermodynamics of Yang-Mills-like gauge theories on S3 times R, the boundary, at recoupling. Of course, this gravitational phenomena that I explained to you in the previous slide is supposed to be manifest as strong coupling, but surprisingly, even at recoupling studies, many qualitative features like phase transition and deconfinement has been found even at recoupling physics. So it has been established that the black holes in AdS is really likely to be the deconfinement quark-gluon plasma. However, due to these weak strong coupling issues, basically all quantitative aspects are different, and it's quite interesting to try to make a quantitative understanding establishing this picture, okay, these pictures. So natural technical question which has been immediately asked, I understand, right after a few years after this was to try to study some supersymmetric black holes in, let's say, in AdS 5 times S5 with maximal supersymmetry from the dual conformal field theory given by maximal super Yang-Mills. gravitational side, and the solution has been first found in 2004, and it has been generalized thereof. But from the field theory side, in the early days, some very important works has been made, but somehow this simple question was regarded to be very difficult for more than 10 years, I understand. And I'll try to explain to you that recently people have found some more clues, and some aspect of this question can be answered in a very simple manner using the index of four-dimensional Yang-Mills theories. Okay. So I'll basically try to, so half of my talk will basically try to explain what has been done more than 10 years ago, and based on that, I'll add a little bit more ideas and try to see more interesting physics. So let me first review very basic properties of supersymmetric black holes. It's very, very complicated black holes. It's much, much more than Schwarzschild black hole solutions. To find this, one had to really use some heavy G-structure-like techniques. It's a technique finding out supersymmetric solutions in supergravity. Or one have to rely on really marvelous insights on writing down the ansatz and so on. So to my eyes, the solutions are really complicated. So I'll just explain to you some salient aspects which will turn out to be important in the later part. So in AdS 5 times S5, the black holes can carry many charges. It can carry energy, and it can carry three internal charges, which are angular momentum on S5, and two angular momentums, which I call J1 and J2, which are the angular momentum on the three-sphere part of AdS. As usual for BPS configurations, the energy or mass of such BPS black holes is given by a linear combination of all these 5 charges when multiplied by the AdS radius. It turns out that these black holes are complicated because it has to have both angular momentum and electric charge, to say it roughly. And roughly the understanding from field theory is the following. If you have 0 angular momentum, only electric charges, the BPS spectrum of the field theory can be sort of completely solved. It's sort of chiral rings, and basically the corresponding operators are consisting of commuting fields, trace of some fields where the order is irrelevant. So roughly you're dealing with diagonal matters, and in this sector it has been well known that there are not enough BPS states to form macroscopic entropy, forming black holes. Similarly, I don't find a very sharp argument, but if you only have angular momentum but no electric charges, most of the, I think virtually all operators are happening to be anomalous if you turn on coupling constant, if you don't have SO-sigma charges.
Sorry, just one more question. In these black holes, in these BPS black holes that you have written down, is it assumed that the horizon is smooth? Does that give new conditions? Or?
Horizon smoothness is assumed in these analytic solutions. But as I'll explain to you shortly, very briefly, there are more generalizations. People are trying to make more generalizations of these black holes by admitting black hole hairs. And the horizon structure is somewhat different from what has been found so far.
So now I should think about this. It is a 5-parameter set of solutions which preserves some amount of supersymmetry.
I'll get to that. I'm getting to that.
Oh, okay.
We're getting to that. but thanks for anticipating what I was. Yeah.
So the GI equal to 0 are like the 1/8 BPS giant gravitons?
What, GI equals to 0? Yes, that's like 1/8 BPS giant gravitons.
And the QI equal to 0 are like the dual giant gravitons?
No. I mean, giant gravitons and dual giant gravitons are both in this chiral ring sector. There are some more crooked type of giant gravitons. So some Q's being non-zero and some J's being non-zero. I think it's discussed by you. What is it? Wobbling? What you done with Nemani, Sriyanarayana?
Yeah, that's about up to 1/8 BPS.
Yes, but both giant gravitons and dual giant gravitons are J equal to 0 states. Q equal to 0, I think the BPS spectrums are even more boring than chiral rings, I feel. I find nothing more than super singletons in this spectrum. So I mean, this is very, very boring sector, I think, in the BPS sector. Yeah. So that's the reason why solutions are too complicated. Both electric and angular momentum has to be 0. It turns out that it preserves so little number of supersymmetries, 2 real among 32. So it's supposed to be accounted by so-called 1/16th BPS states in the dual field theory. And inevitably, the solutions are very, very complicated, so you should have a look at it now. Okay? I'm not showing solutions at all. 2 properties that I have to mention is that They have 5 independent charges, so naively one expects 5 parameter solutions with 5 charges. It turns out that for certain technical reason, having to do with the smooth event horizon and so on, it's quite characteristic features for many other BPS black holes. They only turn out to have 4 independent parameters. So 4 independent parameters having 5 charges. So on the space of these black holes, all these 5 charges are always happening to satisfy a complicated charge relations. Okay? I have no physical reason why that has to be the case intrinsically from field theory, but it will be important to know later if you try to explain these black holes from field theory.
So 4-parameter family of
supersymmetry.
Preserve supersymmetry, some amount of supersymmetry,
Mm-hmm.
and they have regular horizons.
Regular horizons, yes, yes, yes. This condition is quite crucial for killing one parameter. Well, it's even the same for flat space BMPV black holes and so on. One combination of angular momentum is somehow forbidden by this horizon smoothness requirement.
And no closed time like curves.
Oh yeah. But
these are all extreme.
extremal and BP, yes, sure. Yeah, it has 0 Hawking temperature.
They still preserve only 2 supercharges.
2 supercharges, yes. And an interesting generalization has been made, generalizing the works of hairy black holes in AdS 5 times S5 by Sayantani, I think. Sayantani, Shiraz, and, Papadodimas. Oh, gosh. Sorry, this is Kyriakos Papadodimas.
Sorry, these
Yeah.
4 parameters set of solutions, they're automatically extremal.
Yeah, 0 temperature, 0 Hawking temperature. It's extremal, yes.
And
It's a special codimension 1 set of extremal black hole solutions in AdS 5.
extremal black hole solutions are coming in general. Extremal black holes which are not preserving supersymmetry, they have how many parameters?
I think 5, right?
They have
They're
5.
characterized by charges, yeah.
They have 5, and then this is the set which is common to both.
This is the,
Common to supersymmetry.
yeah, this is a subset. This is the codimension 1 subspace of this extremal black holes solution space.
And all extremal black holes have nice causality properties. Like they are nice. Like 5-parameter
Yeah.
set of solutions which are extremal,
Yeah.
and they have no properties like smooth horizon.
Yeah, of course, yes. The recent studies that I'm going to mention have a slightly singular horizon property, at least in the BPS limit, explored numerically by Santos and his collaborator, Markevich. They have found more general solutions than what has been found by allowing certain charged fields, charged under these quantum numbers, to condense outside the event horizon. And by allowing this, they found numerical solution, BPS limits of the numerical solution, that has no charge relations. Okay, so it apparently seems that 1 more parameter is allowed, but the price you have to pay is that it has a mild horizon singularity. It has metric finite at the event horizon, so you can properly define Bekenstein-Hawking entropy and so on. But if you take more and more derivatives, it has mild kind of singularities. Okay, so I think it's quite likely that this kind of solution has to be included in the full discussions of thermodynamics of AdS CFT. So these are more recent generalizations.
And if you turn on infinitesimal temperature, the solution smoothen out, right?
I think so. Yes. Yeah.
So that suggests that they're physical.
Yes.
So these the last one,
Yes.
these ones have some mild singularity at 0 temperature.
Yes. That's what I read from these numerical studies.
And they have 5 parameters. Is it?
To be more specific, turning on all 5 parameters is very difficult for numerics. So they consider a subspace of solutions where Q1, Q2, Q3 are equal, J1, J2 are equal. And in this subspace, previous studies failed to have 2 parameter solution, but just 1 parameter solution. Just number of parameters used to be always 1 less than the charge that you turn on. But they have found a 1 parameter generalization. So 2 parameter solution for two independent charges. So you just call this Q and this J, and they found 2 parameter solutions.
Roughly like 1 parameter roughly.
Yeah, finding 1 more parameter than the previous ones. Okay. So far I have no direct access to this kind of black holes from field theory, but from novel larger and saddle point I will find, we'll have some features somewhat similar to this, so I'll have to recall this later on. Anyway, the black hole side was brief. Let us get into field theory. It turns out to be, to my eyes, much easier. So I'm going to study, with all this motivation, the degeneracy of BPS local operators or BPS states on S3 times R of maximal super Yang-Mills. But if you're just going to do a naive study of thermal partition function or partition function with chemical potentials turned on, it's still difficult. If you just do weak couple calculus, there's no guarantee that the spectrum captured there will continue to strong coupling. So more easily, we're going to study a Witten index type partition function S3 times R. It's called superconformal index and has been developed, I think, right after the gravity solutions has been found by Romelsberger and then by Kinney, Maldacena, Shiraz, and Sufrat Raju in 2005. But always, if you study the Witten index, it counts the number of bosonic states, some supersymmetric bosonic states, minus the number of fermionic states with -1 to the fermion number inserted in its definition. So if you're going to do this kind of analysis, you always have to study things at the risk of potentially losing certain interesting information by boson-fermion cancellations. It will be important to understand this subject later on, so I emphasize this. Okay. So anyway, the definition of index was given as follows. It's the usual partition function taking trace over the Hilbert space of the quantum field theory with the insertion of -1 to the fermion number, so that we are going to develop a quantity which is supposed to be independent of the continuous coupling constant of Yang-Mills theory. And you weight the states in the trace with various weight factors by the non-negative or positive charges carried by the BPS states, and you introduce various chemical potentials which are positive. To make this into an index, the 5 chemical potentials conjugate to 5 charges have to satisfy this constraint because you want this weight to commute with the 2 supercharge preserved by these BPS states in order for this to enjoy the property of an index.
Delta is SO6 cartons?
Deltas are cartons of SO6 argument.
Omega is SO4.
Yeah, SO4, the J1 and J2. Okay. So this is we just impose this because otherwise it's hard to compute. So it's a 4-parameter partition function or index counting BPS configurations, preserving 2 supercharges and carrying 5 independent charges. Okay. So these are all positive charges. So they're positive charges, and these are all playing a sort of role of the inverse temperature, being positive. Okay. So being an index, you can compute it easily from free theory limit of maximal super Yang-Mills, let's say with UN gauge group. And these authors immediately found a matrix integral expression for this partition function using the weakly coupled Yang-Mills theory. Okay. So it takes a complicated form, but roughly speaking, just to explain the structure roughly, the function appearing in the exponent is nothing but what's called the single particle partition function, single particle index. It's an index carried over all the infinite modes of fields. So it's roughly speaking, it's like a single particle partition function. You make this summation and exponentiate. Technically, many people nowadays call it plathistic exponential. It's just imposing the Bose-Fermi statistics to convert the single particle partition function into a multi-particle one. So yeah.
This integration is over alpha AB?
Was alpha AB is going to, so I'm going to explain now. But what we want to do is to count gauge invariant states, not just general multi-particle states. So what one does is to weight all the fields by its gauge fugacities. You want the n fugacities. So all the gauge fugacities come in alpha A, where A runs from 1 till n. And A alpha beta, is a shorthand notation for the difference. Because all the matrix modes, they're all in adjoint representation. So all the matrix modes are being charged with 1 cartan and -1 for another cartan. Okay? And with this weight given, the simple way of projecting yourself to gauge invariant spectrum is to do certain integration with certain measure, Haar measure inserted. So these are all the eigenvalues of a unitary matrix. Exponential of I alpha is an eigenvalue of a unitary matrix. So this is called the unitary matrix integral. Okay. So with this concrete expression given, we have to ask 2 questions from now, which I'll try to gradually answer partly. So the first question is, does the large n limit of this index agree with that of BPS gravitons on AdS 5 times S5. So note that the low temperature means the following. So I said that all chemical potentials are formally playing the role of inverse temperature. So if you take these deltas and omegas to be large enough, it corresponds to low temperature. If you gradually reduce that at suitable ratio, it will be corresponding to going to higher and higher temperature. It's an analogous to low and high temperature limit behavior in BPS sector. So this is the first question. Is the low temperature phase agreeing with the graviton phase in AdS 5 times S5. And if this question is answered, the second question is that if you reduce all these chemical potentials suitably, does it undergo a deconfinement transition and exhibit some behavior similar to black holes? There are the two questions.
This can be considered as supersymmetric partition function on S3 times S1 of some certain radius. Let's say tau. The tau doesn't enter in the formula.
Tau is what?
So you can consider S3 of unit radius and
Yeah.
S1 which is in radius tau, let's say.
Yeah, yeah,
So
yeah.
then the tau will not enter this formula.
To be defining this path integral like expression in Euclidean field theory properly, it will be safer to introduce certain regulators, which includes your tau or something, or we call it beta. And if you include this regulator, it will appear as the circle radius. But since it's a regulator, I just erase this part. Okay, so
That you said it does not.
yeah.
Is this QQ then?
Yeah, exactly. QQ anti-commutator, but just for the simplicity, I omitted it. Sorry if I caused confusion about that. You have any idea? Roughly can be understood as this partition function. So these are two questions. Any other question? So these are all basically reviews for.
Sorry, I missed the reason for putting this constraint.
This one.
Yeah.
Okay, so
Say it again.
okay, so the supercharge that is associated with this BPS state, a supercharge, let me call Q, has particular values of these internal charges and angular momentum charges. And I didn't explain my notation, but they carry Q1, Q2, Q3. My notation is that they are all plus 1/2. And the angular momentum J1, J2 carried by the supercharge is minus 1/2. And the requirement that this measure commutes with this supercharge can be examined by acting these operators on Q and demanding the eigenvalue to be 1. So you insert plus 1/2 here, minus 1, plus 1/2 here and minus 1/2 here, and demand that the exponent to be 0 up to periodic shifts, and you get this. This is plus 1/2, plus 1/2, plus 1/2, minus 1/2, minus 1/2. Yeah. So only when this is met, the measure commutes with the supercharge, this becomes an index. So it's an intrinsic loss of information because we want to compute things easily at recoupling. Yeah? Good.
So it would be easier to see with the regulator.
It's easy to what?
Condition that the chemical potential should map to 0.
Uh-huh.
So this is the standard manipulation index when we write an index that we differentiate with respect to parameters.
Well, yeah, but the regulator is automatically commuting with this, so it's separately commuting with this. Yeah.
It's just a statement that if you want an index to preserve a certain supercharge, the thing that you weight with has to commute with that supercharge. The thing that you weight with is this omega delta. It has to commute with the supercharge.
So that boson fermion pairs cancel.
So that they cancel. Even the naive requirement requires this. Forgetting about subtle.
Okay, so
So this integral looks, I mean, the argument you said to arrive at this integral is very similar to Shiraz's paper on the Hagedorn transition.
yeah. It's precisely index version of that.
So where is the minus 1 to the power f getting into this expression?
Minus 1 to
I mean, in the sense that the fact that it's an index
minus 1 to the power f. For instance, if you look at this numerator terms, it's sinh, so if you expand, you have positive terms and minus terms and so on. So the minus terms are roughly speaking coming from fermions. So if you evaluate this, and if you express everything in terms of fugacity, e to the minus delta, e to the minus omega, you get lots of minus terms in the numerator. Roughly speaking, some of them might be coming from bosonic constraints, but many minus terms are coming from fermions.
Just to say that again, I mean, if we were doing the partition function, this thing here, let's say we were just doing bosons, this thing there would be the single letter partition function.
Yes.
The same formula works when you replace that by the single letter index. So that bracket there is the single letter, is the index over single letters. That's where the minus 1 to the other.
So that's why we can read it off. The
Very
fact that
simple.
there's a
Okay, so any other questions about this? Okay. Okay, so still is a review of what Shiraz did. Okay, so to answer this question, we need a nice way of handling this large n number of these eigenvalue integrals. And the basic idea, which I think has been a standard technique in large n matrix model, is to replace at large n the large number of these eigenvalue integrals to the functional integral of this eigenvalue distribution. And that can be seen easily by regarding these coordinates alpha, these are all periodic variables, 2 pi periodic variables, as some coordinate of n large number of identical particles on a circle because they are periodic. And if in the larger n limit, these particles position will be forming a dense distribution of particle on a unit circle, so that you can replace the integrals over these n identical eigenvalues by a functional integral of suitably normalized distribution function, where theta is the coordinate of this circle. Okay? So more conveniently, in certain cases, you can Fourier expand this distribution function of identical particles in the following manner on the circle. So this is the uniform part, this is the fluctuation part of the distribution. And what one gets is that in the functional integral form, the exponential measure that I wrote in the previous slide gets nicely approximated into some Gaussian-like vectors of these Fourier modes. Okay? And this type of exponent is nothing but this part. And you have to also exponentiate the Haar measure and replace it by a distribution variable. And this turns out to roughly cancel this part, so you only remains with this ratios of Sinches, which I rewrote this way. So supposing that this coefficient is positive, you can simply make a larger and approximate calculation of these Fourier modes just using the Gaussian path integral. Okay? So the question is that, first, to answer the question, you study the low temperature region, and I told you that it's a region with large deltas and large omegas, inverse temperatures, and it's 1 minus small number, 1 minus small number, so coefficient is positive. You can do the saddle point integration of rhos, where all rhos are localized to be 0 at the saddle point. So you're getting a saddle point given by uniform distribution of eigenvalues. And this is really the confining phase of gauge theory. It's in both these index version or partition function versions. And one way to easily see that is to just plug in this saddle point value, rho equals to 0. And the exponent, the classical, semi-classical free energy, is n squared times 0. So it scales like 0 power of n. So it is one signal that this is going to be the confining phase at low temperature. There are many other ways of seeing that in terms of Polyakov loops and so on. So the confining index agrees with BPS graviton index on AdS 5 times S5. So the first question is well answered. Now let us get to second question. In this kind of formulation, if you are to have a non-trivial free, semi-classical free energy scale liking S square, you'd like non-zero condensate of these coefficients. But having a look at this coefficient in the index, no matter how small you take deltas and omega, inverse temperature to be small, it's always positive, somewhat funnily. So apparently the index seems to be never seeing a phase in which these rhos are condensing. If this had been negative, it will be a flipped Gaussian, so rho will want to condense. You'll have a free energy which scales like n squared. But apparently it doesn't happen in the index. Okay? And I'd like to emphasize that this conclusion is obtained when all the fugacities are said to be real, which I claim we have to relax. Okay? Anyway, when this was discovered, I think the natural and apparent explanation for this was that apparently the index is not seeing the deconfinement transition in the BPS sector because there could be a severe cancellation between bosons and fermions. So the bosonic degeneracy could be exponential of n squared times certain number, macroscopic. Fermionic degeneracy could be also exponentially large, exponential of n squared times certain number. But due to this -1 to the fermion number, it might happen that after the cancellation, you're only observing a boring spectrum, so that apparently the index doesn't see the deconfinement transition, which might be visible if minus is changed into plus. Okay? And I should really emphasize, this is I'm going to try to provide an interpretation of this cancellation and clearly dividing two different possible notions of cancellations. I think at least many people around me just imagine the naive meaning of boson-fermion cancellation. So if you expand the index in fugacity, there are many fugacities, but for schematically, let me just write one and one charge, but there are 4 different combinations of fugacities and charges. if you make a fugacity expansion, you want to investigate the degeneracy at a given charge. If the cancellation is such that the Bose-Fermi cancellation happens at each order, then it might really be that index is useless to study the large and deconfined behavior of the gravity dual. But I think it's not my opinion, but I mean, having done all the calculation, I realized that during the past many years, many of my Indian colleagues have been alluding to this kind of cancellations, like Ashok Sen or Shiraz Minalla. So I think they were sort of anticipating what was going on, but I'll try to explain to you my understanding of a second version of a circular cancellation, which can be happening between bosons and fermions. Okay? But I was, yeah, it's not, I don't think it's my independent opinion.
So,
yeah.
sorry, one thing. That formula for the index
This one?
has only rho square exactly, and if, there is no issue of introducing interactions to get some, rho to the power.
Interactions of rows?
Young-Mills interaction.
Young-Mills interaction.
It doesn't make a difference because it's an index.
Oh yeah, it's an index. Yes, yes, yes. If it's a partition function, I understand. Yeah.
It's exactly local minimum. I mean, it's exactly minimum all the time.
Yeah. Later on, there might be certain, but in this setting, it's exactly local, exactly the minimum. Yes.
At least the previous formula is completely 100% exact. Yeah, the previous formula in terms of the eigenvalues.
This one. Oh no. This one.
This
yes.
is 100% exact.
Yes.
Now there may be some strange subtlety in going to the eigenvalue distribution.
Yes. Yeah. Good. So let me try to explain to you the possible certain natures of boson-fermion cancellation. So I'd like to explain the point with an example. I've decided to make a fugacity expansion of U2 maximal super-Young-Mills theory at large charges. For the simplicity of presentation, I keep all internal charges to be same, all angular momentum to be same, and only keep one fugacity for which behaves like temperature. Okay, I would have wanted to do a large n index and expand it order by order to very, very high charges, but that's difficult. But I think explaining in terms of U2 index will be enough to deliver my point. So I expand the U2 index of maximal super-Young-Mills theory to quite high order of charge order. Okay, so one is the ground state, vacuum, and these are all excited states, BPS operators. And if you go to a reasonably large sector, you see that the degeneracies are growing. I mean, I don't know, I didn't estimate how fast it grows, but it's definitely growing. But with this randomly alternating plus and minus signs. Depending on the charge values, it might be fermion dominated or boson dominated. It's not a regular alternation as far as I can see, but it randomly alternates. And consider what one would expect to get if one tries to make a semi-classical approximation of the inverse Laplace transformation, extracting out definite coefficient degeneracy at large charge. Let's say macroscopic charge when larger n limit, or in U2 theory, just large charge. Okay? You can use semi-classical approximation to do this integral. And when charge is very large, these are all angular momentums on AdS 5 times S5. As far as I can see, it's very difficult to imagine that the Legendre transformation problem at large charge will be sensitive to changing J by a quantum. Okay? So in order to see the distinction between this, let's say J is very large, I mean 3 million or something, we have to distinguish 3 million and 3 million plus 1 or something to distinguish whether it's really bosonic or fermionic, which order we are counting. But it's depending on the small changes of macroscopic charges, the degeneracies are wildly oscillating. So the natural possibility that I can imagine about this kind of calculation is, firstly, it may be unable to capture a single omega in the middle of this wild oscillation. Perhaps one might be counting a smeared out version of nearby omegas. That's one possibility I can imagine. Or can we do some calculations better to extract out a macroscopic entropy, exponential of some fastly growing entropy as a function of charge and n, perhaps being able to see the wild oscillator part as well. Okay? So this will be interesting possibility. This might be boring possibility. So if this happens, it might be able to explain what happened explain the true nature of this apparently boring behavior of the index. That's my claim.
So if we stick to real chemical potentials and we go to the eigenvalue distributions, that automatically seems to be doing smearing. Is that right?
I think so. I think so. I think so.
So that was what I think he was alluding to in response to your question. Like somehow this going to this eigenvalue distribution is a continuous kind of thing, which does this smearing. Which is of course impossible with partition functions, because everything there is positive.
That's right. That's right.
That's the intuition we approached.
Yeah. Of course, in the partition function, the expression in what Shiraz did, Aroni and Adar, the function appearing here naturally goes negative if you reduce the temperature, but in the index, somehow magically it remains positive. Yeah.
So this million term and million plus one term, because they are joined together when you go to the density rho theta variables, so they can cancel. This is the.
Yeah, roughly that's what I think. Yeah.
Yeah, this rho theta variable somehow is appropriate for averaging over things of order small compared to n square. It groups together clumps that are alpha times n square, where alpha is very small.
But tomorrow I'll try to explain that even by employing this naive eigenvalue distribution language, if you employ an idea that I'm just going to explain, you can see some hints of obstructive cancellation between bosons and fermions and see some macroscopic entropy. That will be the subject of tomorrow. But anyway, what I'm going to claim is that if you see these wild alternating objects and try to extract out something more useful, I'm trying to suggest that we can partly obstruct these cancellations of smearings of nearby omegas by turning on the phases of fugacities and judiciously optimizing its value. Okay? So minus and pluses, note that it's nothing but a special case of phases, right? So had this minus plus oscillation has been very regular, odd order minus, even order plus, you can just tune x, change x to minus x just to make everything positive. Here it's much more random, but I think it's I thought this was worth giving a trial to generalize the fugacities all to a complex value, trying my best to obstruct this cancellation, okay? And ideally tune that with order 1 phases to see whether get something more interesting or not. So that's a very simple idea. You might think it's stupid, but just sit down and work on it, and it turns out to give much more interesting results.
So could I ask, so suppose as you said, suppose there was a particular frequency, then clearly turning on the chemical potential to that frequency calculates, turns every coefficient positive.
Yeah.
However, if you're even a little bit off from this,
yes,
you appear to be underestimating. You appear to be still leaving room for cancellation.
Yeah. So generally, what I expect a priori is to get a better lower bound for the two degeneracy. I mean, index always is a lower bound, and that's my general point of view. And in the lucky case, if that lower bound turns out to saturate Bekenstein black hole entropy, one can claim that one counts it from the index.
So you would presumably saturate it at some particular complex value of the chemical potential?
Yes.
And that would give you a prediction for the phase of oscillations of these sites?
Yes. Actually, it's interesting thing is that I'll be presenting to you a Cardi formula, and in all these kind of internal space, so omega, so in this internal charge chemical potential, let's say Q1, Q2, Q3 are all equal. The funny thing is that the imaginary part of this I get is 2 pi I over 3. Rather than being 180 degrees for -1, it's 120 degrees. So I think this predicts some pattern of this plus minus oscillations, but that has to be worked out more carefully, I think.
And you're going to tell us, but just to get context, so it sounds like what you should do is to take the imaginary part of this chemical potential and extremize over that as well.
Yes, exactly. So if you work on the complexified chemical potential space and seek for the complex chemical potentials, you find a much more interesting saddle point, and that saddle point will turn out to be black holes.
And you have to extremize over that complex.
Yes, definitely. Yes.
To get the best locking phase.
Yes.
Is this what is usually called I extremization in literature?
I understand that I extremization contains many things. I extremization also, it appears in various contexts of black holes, topological black holes or different black holes. It includes, as one ingredient, using complex fugacity. I think it's one ingredient of what people say I extremization. Yes.
Even if you extremize with respect to all chemical potential, you might not get the actual answer because
it's a lower bound.
it's
Lower bound.
lower bound.
Yeah, in principle, it's a lower bound. If it saturates something that we know under gravity, only then we can claim that the index counts. You know, it's all the same in all index business, unless you argue that the index particularly tuned gives purely bosonic states. Unless you have an independent argument like that, index, I think, is always a lower bound in general.
And one more general question that you're probably going to answer. But you know, if there is a particular imaginary part of the chemical potential that in some sense really characterizes these black holes, then the gravity should also see that imaginary part of the chemical potential. We should, from the gravity solution, be able to pull out that the actual chemical potential has this imaginary.
Well, we are, well, I don't know, but we are inserting these imaginary parts because we want to try best to erase the -1 to the fermion number. But black hole doesn't know that. I mean, it's only our technical setup, right?
I see. So you say, so suppose I stuck to the space of supersymmetric black holes somehow.
Yeah, yeah. But they still don't know -1 to the F.
They
right?
still don't know -1.
Yeah.
Suppose I was doing a gravity calculation for a Euclidean gravity calculation for the index.
With some -1 to the F
With a
insert.
-1 to the F.
Okay.
At least that should see this.
Okay, okay, I agree. Yeah, yeah, possibly. Possibly.
I'm just saying it would be nice to get, if it's something that really characterizes the black hole, it's a physical thing. Right?
Yes, I think so.
It would be nice to get that out.
Yeah, -1 to the F version of black hole. You imagine
Yes.
that? Okay.
So what calculation you do in the gravity? Sorry again.
Suppose you take the Euclidean partition function of gravity with the appropriate boundary conditions to make it an index. So you will be saturated by some Euclidean saddle point, and that Euclidean saddle point should know that the chemical potential was not real but it was complex, and had this complex part, I think. I mean, at least it would be satisfying.
Yeah, I'm a little intimidated to try because this BPS limit of Euclidean black holes are somewhat dirty in its near horizon, right? In the non-BPS limit at finite temperature, it's smooth cap, but I'm always afraid to apply the same Euclidean for BPS.
The dirtiest thing about it is that they become complex.
Oh yeah. Okay. I see. Okay. Anyway, if we agree on trying to apply this idea, I'll try to explain something. So tomorrow, I'll try to explain that the index really appears to see indirectly the deconfinement transition with this idea of complex fugacity. I'll explain that tomorrow, precisely in the context of this eigenvalue distribution and so on. I'll explain that tomorrow. Today I'm going to do something simple for you, because I want to show something quantitative at the beginning. Okay, so I'm at this point I'm going to take a high temperature limit together with large n limit. Probably high temperature limit is more important than large n. For instance, you can just stick to finite n, take the high temperature limit first, and develop something like Cardy formula, and then take large n if you want, supposing that this high temperature limit is more important. So the high temperature-like limit, analogous to Cardy limit I'm going to take is the following. So in the two-dimensional field theory, the temperature which is said to be large, or chemical potential which was said to be small, was tau, which is conjugate to the momentum along the spatial S1. The analogous thing you can do is to take the high temperature limit, or low fugacity limit, for the chemical potential conjugate to the two angular momentum. So that's the most natural thing you can try for higher dimensional generalization of Cardy limit, this omega here. And actually, there have been some studies on such Cardy limit in the 4D index. It has been done by Di Pietro, Komagowski, followed up by Ade-Halley, clearing up some subtleties and so on. But unfortunately, still sticking to real fugacities. Okay? So in this setting, naturally, they don't see macroscopic free energy for black hole either. For instance, in the wide class of models studied by Di Pietro and Komagowski, where small beta is playing the role of these omegas, small omegas, angular momentum chemical potential, the free energy obtained for general 4-dimensional n=1 superconformal field theory is the difference of A and C central charges. With larger N gauge theory with gravity duals, the leading n² proportional part for A and C central charges are all equal. So all you get for this larger N gauge theories is the sub-leading contribution of the partial cancellation. For n=4 Yang-Mills, this is exactly 0, so you get the most boring result, 0. But I'll try to explain to you in the next few slides that a slight generalization of their ideas, just turning on order 1 imaginary parts of chemical potentials, reveals very, very different and much more interesting structure. Yeah, sure.
If you think about this S2 cross S1 index in terms of two modulus, tau
S2 times S1? S3 times, oh, sorry, okay, in terms of two.
S3 times S1.
Two modulus mean omegas.
Yes.
Yes.
S3 times, this is like the one that is written here is like radial quantization and counting the states, and this is the index. So we can also think about this index as partition function on S3 cross S1,
Yeah.
and we can imagine S2 cross S1 has two modulus, one is tau and one is sigma, and then one takes tau to be small and gets S3 supersymmetric partition function.
S3.
S3
Dimensional reduction.
Oh yeah, yeah, small circle. Yeah, 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 yeah.
That has anything to do with this or no? This is totally.
It has to do with this small circle reduction. Today, I'll not stick to that geometric interpretation S3 times S1. Since we have a matrix model, I'll just evaluate it. In the last lecture, I'll stick to this viewpoint of high temperature limit being small circle limit and rederive the same Cardi limit from S3 effective action of background fields. Yeah, so I'll do it in two different ways. Today, I'll not be using this small circle limit viewpoint. On the third lecture, I'll do. Okay? But today, I just have a matrix model expression. I just evaluate it in the larger n limit using certain saddle point approximations.
Yeah, a slightly technical question.
Yes.
So, just by waiting on how to define Chern-Simons theory, slightly long, we define Chern-Simons theory for complex level.
Yes.
And one of the conclusions that he makes, and this was a sort of conclusion that was floating around in the literature, was that if you want to define this integral and sort of have it make sense, then you need to go into complex field space, and then you have to look at you know, Morse contours
Yeah.
from various handle points. And stuff.
Okay, okay, okay.
So in the context of the partition function, it was the case that you had an object that was not well defined, and then you had to complexify things in order to make it well defined. Over here, things look slightly different because for the index, it looks like it is well defined and you can calculate something, but you're not getting the right answer. I just thought, I was wondering if you had any thoughts about it.
Not getting the right answer.
I mean, I'm wondering if, my question is like, is this the same as the case with the partition function, or is it different? Because is this index well defined, or
Well defined at what? Real fugacity or complex fugacity?
real fugacity?
It's well defined, of course. Why do you say it? Witten's argument, Witten's works, I understand, is about the integration variables, like path integral variables and so on. These are just external variables. You only extremize it when you, at final stage, you want to make a Legendre transformation into microcanonical ensemble. So I apparently feel that it's a bit different. Yeah, but the only point I'm going to make is that, yeah.
Between the partition function and Chern-Simons, then the level is
Chern-Simons, where Chern-Simons?
No, I'm just saying, as
Okay.
an example,
Okay.
if you're doing it for Chern-Simons at complex level, then
Yeah.
the level is an external parameter, right? Just like here, you have external parameters. I understand that.
Yeah.
I understand
Okay,
the
okay.
situations that
Okay, so for the Yang-Mills theory, if you introduce complexify chemical potential, it's complexifying the effective action, that's for sure. If you imagine doing the index calculation from path integral of weakly coupled Yang-Mills theory, effective action is definitely getting complexified. But I think the point is that the value of this saddle point in the larger limit of all fields being 0. So perhaps it's less sensitive to the correct contour.
Even a real chemical potential complexifier.
Oh yeah. Real chemical potential complexified. Pure imaginary one makes it safer.
Yeah.
Yeah.
I think at the level of the matrix integral, the matrix integral is written in terms of alphas.
Yeah.
It's just totally well defined for both real and non-chemical potentials. Would you agree with that?
Yeah, definitely. It's just
No, the contour for alpha is fixed because you're doing Gauss law sequence.
Yeah.
So it's over
Yeah.
unit circle.
Yeah.
It's just
Yeah.
that. The integral over unitary matrices is hard measure.
Yeah.
This.
Yeah.
You take that and expand it.
Yeah. If you forget about path integral and just stick to the combinatoric viewpoint of getting that matrix integral, there's no issue like in contours and so on.
Yeah. So I think that the starting, it's better situation. More clear situation. The starting point is very clear. It's just a well-defined mathematical integral. The question is how to take its large end.
Good.
related question. In other contexts, when we do this integral over the unit circle,
Yeah.
There are some poles which lie on the unit circle and we have to regularize it to
Not here, but
so here it doesn't, that problem does not happen.
here it doesn't matter, but that kind of dangerous possibility will happen if you try to make similar Cardi-like analysis for higher dimensional field theory. Higher dimensional field theory has some integrands given by instanton partition function. It's notorious for having many poles. And in the Cardi limit, they want to approach the unit circle, pushing away all these eigenvalues into complex plane. And I think that will have some important hints on enhanced degrees of freedom in higher dimensional field theory, like n to the cube, n to the 5/2. But that's a very wild territory. I'll just briefly mention that at the last stage. Here, I think it's much more safe.
Here it's all well.
Just a quick comment. If that were to happen, it would mean that one letter is at the edge of being not suppressed.
So this is like an infinite temperature limit.
Okay.
Yeah,
Okay,
yeah.
and with that, at least we completely stayed away from that.
Yeah.
Well, part of our condition was that.
So even in the Cardi limit, you take the inverse temperature to be small, so they will be quite small, closer to the unit circle, but I never allow to strictly be on top of it. Yeah, that's very important. And anyway, yeah. When is the time?
It's lunchtime, 1:15, 1:20.
Okay, I don't have many contacts. So this is the most technical part of the talk. So, but anyway, the key idea is I like to take the large charge limit, meaning that I like to take the chemical potential to be positive and small, but only the real parts. Okay, imaginary part, even in the Cardi limit, I like to keep them at order 1 and take advantage of them at the extremization. Okay, it allows you to probe more interesting saddle points, which is actually corresponding to black holes. So real parts of chemical potential, deltas and omega, will all be taken to be small and positive. The real parts, I want to keep order 1. In foresight, that will be the right setting to do. Okay, keep order 1 imaginary parts of chemical potential. And it will be all a matter of distributing a given phase to order 1 phase to different variables. So I'd like to slightly reformulate the index, if you like.
This is the same statement that the phase oscillation period is roughly order 1.
Yes. So I'd like to slightly reformulate. This was the previous definition of the chemical potential. I'd like to slightly redefine it by converting the effect of -1 to the f partly into the chemical potential. So -1 to the f is nothing but, let's say, e to the -1 to the f. You can write it as, let's say, 2 pi I times any one of these 5 charges, because they're all spinor-like variables. Let's say you can do q1 or e to the 2 pi I over j2 or whatever one you like, because evaluating on fermions, you get -1s. Okay? So by replacing -1 to the f in this form, this kind of phase can be shifted into an imaginary part of any one of these chemical potentials. So the rewriting of these indexes trace without -1 to the f, but the redefined chemical potentials linear combination is not 0, but 2 pi I mod its period. Okay? So now in this, you can do it either in this formulation or this formulation, but things are much neater here, and you get a much better looking result. So here it's quite clear that part of the question is to decide, after getting some Cardi free energy, distributing this finite 2 pi I, coming from -1 to the f, judiciously to these variables. Okay? So I think this is a much better way of studying this partition function, although it's a technical point. So if you do this redefinition of chemical potential, the previous matrix integral slightly changes. This was the previous one. If you do this redefinition, this is the...
I'm sorry, I was spacing out. I missed this going to 2 pi I mod.
Okay, so let's say it this way. -1 to the f. Let me rewrite it this way. Okay?
Oh,
then insert it here, and I can absorb this 2 pi I as a shift of, let's say, delta 1.
Yes.
And then you can do it to any one of the 5. And then this condition becomes, summation becomes 2 pi I because of this, mod 4 pi I shift. Yeah.
So it's just -1 to the f.
Yes. But this turns out to be a much better framework. And anyway, it's just a technical point. It's just personally that I realized what was happening during my project only after rewriting it this way. It's just some personal taste.
Some intuition, like, so -1 is just an ordinary written index.
Yeah.
What is writing it like this do the written index?
What is
What is writing -1 to the f in this form?
What is?
There's some simple quantum mechanical system where I can get some intuition for what is happening.
Quantum mechanical system? Sorry, I didn't get the question.
You're taking the -1 to the f and you're distributing it over all of the chemical potentials.
Just one, I mean, any one of them.
Well, yeah, you can redefine the chemical potential this way by shifting one of them. And then still the question remains, after you get the free energy, I'm having in mind at the after stage of getting the Cardi free energy at given chemical potential, I'm going to convert to microcanonical ensemble, and at that stage, deciding the phase is very important. And it will turn out that order 1, I mean, it will turn out that having non-trivial order 1 phases is important to getting to the right saddle point for black holes. And this formulation, I think, is making this structure very manifest.
And the importance of -1 to the f is that Q anti-commutation. And it does with this charge as well.
Yeah.
It's just that.
Convenient.
Yeah, it's just my convenience. But everything will turn out to be much more symmetric looking in this phases. It's just personal taste. Yes.
So the statement is that whatever imaginary words you get after extremization, they should add up to 2 pi r instead of C2.
Yeah.
That's the
Yeah, that constraint has to be met because we are on the index. Yeah. So in this setting, this is the matrix integral. And in this setting, what I'm like to take is, in this setting, I take omega 1 and omega 2 to be small as a complex number. So at this stage, I'm claiming that I'm forbidding the distribution of these 2 pi to these omega 1 and omega 2, but only to these. I claim that this will be an interesting choice. And afterward, we'll check that this is the setting in which large black hole will be staying at. Okay?
And you're going to take the real part of all of them to be small.
Real part of all of them to be positive and small. Yes.
Real part of delta will also be small?
Yes, I have already explained to you that I want to take large angular momentum, so omega to be small. But let's say for this, I don't think there's a prior reason why you should take real part of delta to be small, but just electric charge not so large, but angular momentum only large. There might be interesting physics in that region, but my primary motivation is to study known black holes. And the known black hole has the property that when angular momentum is large, electric charge is also large, although at different rate. So I'd like to study the point where we expect to have something non-trivial. So I take both electric charge and angular momentum to be large, okay, at certain rates. Okay. So all real parts are positive and small. Okay. And having in that mind, you approximate this matrix integral. And first of all, you do this approximation, and roughly, you can do a more careful analysis, but roughly what you do is when you have a cinch of small numbers in the denominator, it comes from holomorphic derivatives. You replace cinch of small number to that small number itself. Okay? You have to do work more carefully because it's an infinite sum, but it's roughly speaking, it works. So you replace this cinch of n, so numerator becomes n times omega 1, n times omega 2. So there's a characteristic large number appearing here, something like 1 over tau in the Cardiff limit. And the remaining terms is just a polynomial with 1 over n to the cube inserted. So they all get converted into what's called the trilogarithm functions. Okay? So integrand becomes quite simple. Then you have to decide what is the saddle point for alphas. Just at large n limit, you seek for a large n saddle point for alpha. I'm doing the Cardiff limit, and I'll take a larger limit also later, but I'm taking Cardiff limit first to do a simplified calculation. You rely on the fact that charge is large to find a large charge Cardiff-like saddle points for alpha. That is much simpler than just doing large n saddle point analysis. Okay, so I take, yeah.
So there's a 1 in the within the round brackets.
Yes.
So when you just sum over it, formally that looks like a divergent.
Yeah. So you have to do it. That's the reason why I have to do it very carefully. So if you combine this with this divergent part cancels out. Okay. But roughly speaking, I only explained this part, right? So the leading order divergent part in the Cardiff limit, I mean, this certainly cancelled terms don't contribute. So that's roughly why I can ignore this and just work with this part. But we did it much more carefully. Yeah. But roughly speaking, this is only, yeah. But yeah, the two parts cancel in this divergent. Yeah.
So the first step is not an approximation. That's
which step?
That's exactly the
from here to here. Yeah, it's just changing notation. Yes.
So that's
yeah.
exact.
Yeah, from here to here, you take omega to be small.
Right.
Yeah. So this is the characteristic Cardiff-like behavior of the free energy. And now you have to do what kind of Cardiff saddle point you'll take for this unitary matrix eigenvalues. Now, when I was doing this, I thought that it would be naturally the maximally deconfining saddle points, okay, where all alphas are equal. So I didn't explain that it's a point where the kind of Wilson-Polyakov loop expectation becomes maximal. I thought it was natural value. Clearly, it turns out to be a local saddle point if you extremize this effective action. I assume that it's natural to be, I thought it was natural to assume it like a global saddle point of at least in the Cardiff limit. Okay? This Di Pietro Komagowski in the same setup assumed this and got in good results. And I think similar kinds of maximal deconfining saddle point was assumed in Shiraz's paper early on with Aharoni et al. In the context of eigenvalue distribution, I understand that they got intuition from this high temperature limit of Gross-Witten-Wadia model, where after the phase transition, the eigenvalue distribution gets narrow to a delta function-like distribution. That's really the maximally deconfining distribution. So at the stage of writing my paper, I assumed that, naturally assumed that it's a dominant one. Last week, there appeared a paper by Masazumi Honda, who says he proved that this is actually the dominant saddle point. So I haven't read the detail, but I'm very tempted to believe that. And assuming that, you plug in this value, all the gauge holonomies are gone, all the matrix integrals are gone, you end up with this simple result. This is my Cardi free energy for maximum. And since there is summation of all the adjoint valued matrices, but the gauge indices are all gone, you naturally get a factor n squared.
So where is the complex part of the chemical potential? Where's the
deltas, and everything is complex.
Everything's complex.
Everything is complex, but I demand omega to have small real and imaginary part both. Delta has small real part, but order 1 imaginary part.
Yeah, so I wanted to see in this formula that if everything was set real, the n square goes away. That's because the
yes. When everything is real, deltas and omegas are all small real number at similar order, so this factor is suppressed to be very small.
Okay.
That's the reason why Komagosky and Di Pietro's result is so boring. They got the result 1 over beta a minus c, and this result was 0. And if you plug in this result, it's beta to the first power, so it's much more subleading than that.
But there's an n square.
N square. So the point is that, just a second. I got this one, and using the trilog identity, which transformed trilog into Bernoulli polynomial in certain range, I get this rational function. And I can see that it's macroscopic n square because of this chemical potential relation. I demanded this to be completely small as a complex number. So 2 pi I has to be distributed to delta 1, delta 2, delta 3. If it's sort of equally distributed, let's say for equal charges it's equally distributed, that happens to be the case, all these three have finite imaginary parts, making it n square times a finite number multiplied by extra large factor having to do with the Cardi limit. So in a sense, I get a large n square macroscopic free energy.
Okay, I just wanted to see that when everything was real, there was no n square.
No n square. N square times a highly suppressed number.
And that highly suppressed number has to be smaller than 1 by n square.
I think so. I mean, I think if this number is small, many of the calculation I made here will be invalidated, I feel. Yeah, yeah.
So there's some limit that.
Yeah. Important thing is that I assume that deltas are very exponential of these deltas are very, very close to a pure phase. That's part of my assumption. I mean, that's part of the approximation.
And that very, very close has a 1 by n square.
I think, strictly speaking, I haven't taken larger limit yet. So it's very, very close by, I think, 1 over charge to some power, I think. So I'm strictly speaking, until here, I'm taking large charge approximation. At the final answer, I'll also take n to be large, but only after calculation is done. So I think that's why I presented the initial 2-dimensional Cardi formula in this too specific way.
But are you saying that even for real chemical potentials, if you go near enough, if you go to small enough chemical potentials, but not of order 1 by n square, we see n square scaling? You're not saying that, right?
At purely real chemical potential, I'm not sure. Yeah.
But where in your formula do I see it? I mean, our way of doing the calculation appeared to show us, unless we messed up even worse than you're suggesting we did, our way of doing the calculation appeared to suggest that no matter how small we took the chemical potentials, as long as there wasn't a 1 over n square or something like that, the answer was of order 1 that function of chemical potentials.
Oh, I see. So in the Gaussian matrix model, the coefficient gets small at high enough temperature. But so if it gets too flattened, you think there will be certainty. So
sure. If you take those coefficients,
I see.
Those things to scale like powers of n, you'll get powers of n.
Yes.
I was just wondering if somehow your approximations could see that.
Yeah. Can I go back to the previous
Yeah.
the linear approximation of the singe?
Yes.
So there is a linear approximation to the singe that you do.
Yeah.
Where this n is n is summed from 0 to infinity.
Yeah. So when n is very large, you're suspecting that that approximation will be invalidated.
In order
Yeah.
to make that linear approximation from
Yeah,
the
yeah,
cinch,
yeah.
you have to put a cutoff to respond.
Yeah, definitely. Yeah.
That cutoff might have something to do with n.
Well, the thing is that if that approximation cannot be made, if that for the first few terms when that approximation can be made, that will contribute to terms of this large number times something finite.
Yes.
When this approximation cannot be made, it's already starting to show an exponential suppression so that those terms will never have chance to reproduce this behavior. So sinh n times omega. Omega is small, but n is of order, let's say, inverse of omega. Then the sinh of omega will start to give exponential suppression or even order 1. So those terms definitely don't contribute this order. So I'm assuming large charge behavior to make this kind of approximation into sinh x approximated into x itself.
Sorry, could you go back to the next slide, please?
Next, okay.
You have this Li minus Li.
Yes.
Now I don't know anything about what these Li functions are, but is it the case that I was just wondering where if all deltas were real, at this level itself you could see that this is somehow very, very small.
Let's see. If delta is very, very small.
If deltas are real.
Real and small.
And okay, yeah, let's say small. Can you see that?
If it's real and small, yeah, real and small, still you can do this approximation, you get this result. But
nothing more. Nothing
then due to this, if it's purely real,
I would have expected to see something special happening when everything is real.
Okay, so in this kind of basis, if you like to take it to be.
Oh yes, you've changed that.
Yeah. Small means small real part, but distribution this in a very special way. Let's say this way. You mean going back to chemical potential in the previous notation? Yeah. That can be done by the following way. Let's say this. Hope I can do it better. So it has all small real parts, and you have to give some imaginary parts. Let's say I think the rule is 2 pi I. Sorry. I'll have to think about it. I once thought about it, but there the result I remember is that it's still highly suppressed. It has still a highly suppressed factor. If you do properly distribute 2 pi I into this so that you get back to real figures in the previous convention, the result I got was suppressed in a similar manner as this.
I just ask one more thing and then I stop and ask you. But
it's okay.
If your original sign of, that you have this phase locking picture, where if your chemical potentials were all real, you could get 0. But any non-zero chemical potential, any non-zero part of the complex chemical potential has the chance of at least slightly unlocking the phases.
Yes.
So I would have expected to see something very special happening for purely real chemical potentials. Something very special. I'm not at this stage seeing that.
Maybe can I try to answer this question tomorrow because no.
Thing would fail, right?
Sorry?
The power 2 pi I cube. If you're taking everything real, this technique itself, this small technical point would fail, and you won't be able to proceed from there. So, this requires chemical potential to have the imaginary part.
Which is this -1
Yeah.
So I'm saying don't undo this trick and then set all chemical potentials.
But anyway, tomorrow I will try to revisit this distribution calculation with complex chemical potential. Real chemical potential definitely is special.
Okay.
And I'll try to gradually turn on the phase and illustrate to you what happens.
Okay.
So I was wondering about the order of presentation, whether I should do that first or this first, but I wanted to show quantitative things first, so tomorrow I'll try to do it. Okay, so anyway, I get this result. This is the Cardi free energy I got with this condition, okay? So if you take for the large n limit, as I explained to you, it has a macroscopic large n free energy with order 1 number multiplied by some large charge extra factors, okay? And then Well, you might have noticed, I mean, if you are good at the Tooth anomalies, these cubic polynomials appearing in the numerator is nothing but the Tooth anomaly polynomial of the SO6, I mean, the Cartan parts of the SO6 R symmetry, if you know this anomaly polynomial business better. So having a look at this part, you might wonder whether there might be more intrinsic derivation of this using Tooth anomalies also, only. So in the last lecture, I'll sort of try to do that, present a more abstract derivation of this Cardi free energy using Tooth anomalies and a little bit of discrete symmetries. And this I think is really similar to the two-dimensional Cardi behavior, where you get free energy central charge divided by tau, because this Tooth anomaly polynomial contains the information of these central charges and so on. So I'll try to present a more abstract derivation of that and apply to, let's say, more challenging non-Lagrangian CFTs and so on. Anyway, this is my Cardi free energy for now. And to really see whether this has the information about black holes, you have to do a Legendre transformation back to microcanonical ensemble and see where the entropy is macroscopic and corresponding to that of the black hole. So this is the free energy, and do the Legendre transformation means that you fix the real charges and extremize this kind of functions. And the result in extremized value of this function will be the entropy of the microcanonical ensemble. All the coefficients appearing in this function is real, but generally you're expecting to get the complex value of this function at the saddle point, because the constraint that has to be satisfied by the index is complex. Okay? So it drives these chemical potentials, some of them to assume complex values. So we generally expect to get imaginary part. Okay? One should interpret that carefully. For physical reason, so the degeneracy factor that we should consider is exponential of this complex entropy. And for physical reason, let's say from the unitarity or hermiticity of the theory, we never expect the extremized entropy to be complex. Okay? At best, we expect it to be fluctuating around plus minus 1. So from physical grounds, we expect that this imaginary part would be an integer multiple of pi. Okay? But now we're dealing with macroscopic charges. It's hard to make a direct argument that this should be an integer multiple of pi. Maybe by using semi-classical Bohr-Sommerfeld-like things, one might be able to do that. But we could show it alternatively by using the fact that these chemical potentials are periodic variables. Note that I've been showing to you an expression for the free energy in a particular chamber of the chemical potential space in the imaginary direction. If you go beyond that, you get an alternative expression, forcing the free energy to be periodic in this imaginary direction. So it has a mild cusp. And using this full structure of this chemical potential dependence in the full imaginary directions of the chemical potential space, you demand the periodicity, or you use the periodicity of the chemical potential. You can argue that this imaginary part really should be integer multiples of pi, so that it really has a chance that our calculation is giving you the macroscopic entropy given by real part of S, and it really sees the possibility of wild oscillation between plus and minus ones. But we don't know when it happens to be plus, when it happens to be minus. It just allows this possibility. Okay?
This is supposed to reproduce entropy for which black holes? All the supersymmetric black holes, this 5-parameter set of black holes which has a singular structure.
Singular what?
So this 5-parameter set of black holes had slightly singular horizons, but 4-parameter had done everything nice.
Well, I think 5 parameters, I mean, the more general solution is still nice because, entropy is finite. I mean, area is finite. It can be interpreted as back-engineered entropy. And from field theory side, maybe one day, from field theory microscopically, one may be able to characterize the formation of hairs or not. Do you know what? Really, if you can see deep inside the bulk from boundary field theory, you may be able to assess when the hair exists, when the hair does not. I don't know that yet. So what I'm going to do is the following. I'll explain the next slide, practically what I do. So anyway, real part of S provides a lower bound of the 2 BPS entropy in the general. If in particular cases, if we find real part of S saturating the back-engineered Hawking entropy of known black holes, we can claim that we have counted them. Okay? And now I'll explain what I did. Now, numerical solutions I try to compare, but to be more precise, the numerical solutions about the BPS hairy black holes are all found in small black hole regimes. For some technical reason, I asked to George Santos, but he finds it difficult to do it for large black holes. So to do the large black hole comparison, I can't compare with the known hairy black holes so far, because all of them are small ones. I just compare with the known analytic solutions of black holes with better shape of horizon and so on, which happen to have charge relations. I've seen no reason for this charge relation from the CFT boundary dual. Maybe it has to do with the absence of hair condensation, but I don't know. All I can do so far is to impose this condition, charge relation, on the field theory free energy analysis I did, free energy entropy that I computed, and see whether it agrees or not. There I find agreement. More concretely, if you impose this charge relation on the extremized entropy, the real part of entropy, you naturally get two alternative expressions for the entropies, because there are charge relations. If you try to write it in terms of independent charges, there's always ambiguities. There are two natural expressions that we can write down out of this extremization business. The compatibility of these two expressions is the charge relation. The first expression I showed with Kim Young Lee many years ago. That is the expression for an expression for the Bekenstein-Hawking entropy of known black holes, analytic black holes. So this established the fact that our free energy, with charge relations imposed, explains the entropy of supersymmetric AdS black holes, so known black holes, okay, in the large n limit, and a large charge limit. Okay? So I impose this charge relation by hand. One interesting fact is that during this extremization procedure, we derive this expression for when omegas are small. Oh, so the saddle point has complex deltas, and let's say for equal electric charges, the imaginary parts of all deltas are 2 pi I over 3, equally distributing this 2 pi I. Okay? So that's the reason why we get macroscopic entropy, and it's positive. Interesting part is that I derive this free energy only in the Cardi limit, but once you accept this functional form, the extremization of this function accounts for known black holes even away from Cardi limit. So it's quite similar to the fact that the naive application of Cardi limit in these two-dimensional CFTs gives this result when P is sufficiently larger than something, let's say central charge or something. But still, this formula is true for the same black hole away from the Cardi limit, when these three charges are equally large or so on. Okay? So I think this is a very analogous phenomenon happening in these known analytic solutions of BPS black holes. They're somehow nice that their thermodynamic properties way away from Cardi limit somehow can be at least formally derived from the Cardi formula, so on. Okay? And this kind of behavior will be somewhat important technically in the next lecture. Good. So let me briefly conclude. I tried to explain to you that with a little bit of extra ideas on phases of fugacities put in, the index of four-dimensional CFTs, let's say maximal Young-Mills, sees the BPS black holes in AdS5 times S5. I had tried to explain this by developing a kind of Cardi formula in the large charge limit and counting known black holes in the large black hole limit as the dominant saddle point and the maximally deconfining saddle point. Tomorrow, away from this limit, I'll try to explain to you much more exotic things may happen, sort of predicting new black holes and perhaps similar to hairy black holes and so on. Okay? I think one of the important questions to answer is that the following thing. Since we computed the entropy of black holes from the index, in principle there should be enough information in the weakly coupled Young-Mills which can probably tell us which kind of operators are responsible for these black holes. Okay? I tried to work on this with Shiraz and Lars Grant. Shiraz is ex-student, and Pietro Grassi. I don't think we get any close to constructing actual black hole states. There has been more systematic studies by Chimin Chang and Yin, and there's some numerical studies of U2 and U3 indexes up to reasonably high order of energy. I'm not really sure how high they went, but they did systematic calculations. But still, nobody found actually what kind of operators are explaining the entropy of these black holes, at least in the large black hole limit that we identify. So I think this will be perhaps one of the most important questions and actually puzzling question.
I was going to ask you about that. So,
Uh-huh.
in your enumeration of the indices at
Yeah.
U2, that should have some overlap with Chang and Yin, right?
I think so. Yes, yes.
And my understanding was that they concluded that every state that they could find was basically just
Yeah.
multigravity.
Yeah. So I try to look at their tables very carefully. Let's say so one has to really investigate how high order in this charge they've got. U3 they didn't go very large, I think, but U2. I think I have to understand. I mean, the charge combination appearing on top of Fugacity is Q plus J something. So really have to carefully estimate. Maybe for U2 they got up to charge of 10 or something. I vaguely remember. I'm not really sure whether that's large or not, but it's way larger than N2 square. So that.
It's not so much.
Yeah. So that's very puzzling.
Just to repeat that question, you just enumerated the index numerically. You enumerated the numbers. Now, if you just compare with the black hole formula, n equals 2, and roughly, if you start seeing where it starts agreeing, that will give you an estimate.
So I did a very conservative thinking and gave up that calculation because of the following reason. But I think even for charge 30 something, I have to do that. But earlier on, I had the thinking of the validity of the Cardi behavior. I mean, I robustly reproduced this entropy in the Cardi limit, where charge is large, and that has to do with omega being somewhat small. I don't know what small means. So let's say omega being, let's say, absolute value of omega being, let's say, 0.1 to be small. Well, I think it's the marginal point when we can regard it as small. But the extremized value of angular momentum, if you do the extremization, is something like cubic of this, if you do the calculation. So if you accept this small, our Cardi regime is attained at angular momentum charge at 1,000. So definitely I can't expand things up to Cardi order, but still something special can be happening even way below this order. So, well, if I can expand things up to 100 or something, I would expect something nice might happen. Yeah. But I think it's doable. I mean, this 30 order something, I did it without any problem to 20 order myself. Higher than this, I got stuck. So I asked my ex-student, Juno Kim. He's very good at computer, but he got to this order in, let's say, 15 minutes or something. Okay. So if you really, really try hard, I don't know about computers, but maybe 100 order this. Yeah, I think even this order I should do experiment. Try to see if I think something interesting.
Exactly. You can just take the gravity answer and make a prediction for the index from there.
Okay.
And compare against this.
Yeah.
See if they start.
I think that's interesting. I think that's an interesting thing to do. Yes.
Yeah. Can I just make a comment?
Yes, please. Yes.
Yeah. So I mean, I'm not sure that if Cardi limit is the right limit to take, because it seems to me that what one should do is to also take large n, right?
Yes.
So numerically, if one wants to test the formula, the black hole formula, one should take n large and charge is large.
Yes.
Right? That is the real black hole regime.
Yes. I have to take n large.
So has anybody looked at?
Yeah.
Yeah, n large. So basically, what you need to do is to take n large, take 4 of the charges large, and then trace over the other, the 5th one, because you are calculating an index, right?
Yes.
And that's what one should compare with the black hole entropy formula. So has that been done?
Sorry, can you explain again?
Aim to be not 2 or 3, but say 7 or 8, right? And take the charges appropriately, not take the Cardi limit.
Okay. So you're asking about similar. You're asking about similar kind of expansion, but not n equal 2, but reasonably larger one, like 7 or 8.
Exactly. Yeah. Exactly. Numerically, right?
I see.
Because for flat space black hole, certainly this comes pretty close to the black hole entropy. If one does similar analysis for flat space black holes,
I see.
Not take the Cardi limit, but take all charges large.
I see. 7 or 8, I'm sure it will be technically much more complicated, but hopefully not formidably complicated. I haven't done it, but I'd love to.
One more.
See, 7 or 8, but I'm not saying that you also take the charges to be 7 or 8. You don't go up to 30.
Oh,
Right?
I see.
So one more related comment. If one can just start seeing where the coefficients of these things start scaling like e to the power n square, that's sort of like black hole. That's like the onset of black hole behavior. So if one can do the same calculation but at 3-4 different values of n, and see the n scaling, that has a lot of information.
I see. Okay. Thank you.
Yeah. It may even happen that the result will come pretty close to the classical black hole entropy, because at least in flat space calculation, if one does a similar analysis of up to n equal to 4 or 5, taking all charges to be large, just numerical counting brings you pretty close to the black hole entropy.
I see.
Not the entropy. If you take the log of the degeneracy, that comes pretty close to black hole entropy.
I remember that one. I'll try something like that. I haven't done it yet. Yes. Thank you.
Thanks.
So that's basically it. This is just what I'll try, summary of what I'll do in the next 2 lectures. And I finished my talk. Thank you.
Okay, questions, ICTS? No, there's someone.
No questions.
Okay, thanks. Questions, HRI?
Questions?
Oh, we are fine. Thanks.
Questions, Mumbai?
About the complex phase, so it seems that, let us say you start with the index thing, Shiraz's calculation, and then you do an inverse Laplace transform. I mean, what I'm trying to say is that the amount of phase that, so you do a saddle point calculation, and then you find that the saddle point is complex.
The saddle point value of this chemical potential.
Saddle point value of this chemical potential is complex. And am I to understand that it becomes actually the actual entropy? Okay. Normally, if you start with the index and do an inverse Laplace transform, what you will get is not an entropy. It has nothing to do with entropy. If you started on the other hand with something which did not have the -1 to the power f, then what you would get is some kind of entropy. Now the reason why your reading of entropy from there is that it's like the -1 to the power f, you distribute that in the deltas, and that is precisely the amount of phase that is picked up by the complex saddle point.
But even if that phase is not precisely cancelling -1 to the f, wouldn't we get a lower bound for the entropy by just inverse Laplace transforming the index? Lower bound.
I agree.
Yeah.
But you can't read off quite the entropy from there, right? But
true entropy.
So it's true entropy.
So in general.
So this entropy that you were saying is that
lower bound. Only when I compare with something known in the gravity, and when I find it saturating, I assert it as a true entropy.
Okay.
But I don't know whether there will be a stronger story than that, at least in this context. At least so far,
So I have 2 questions, one related to what Gautam said, and this question is as much for Ashok as for you. Ashok and collaborators in their earlier papers had some gravity understanding for why the index was equal to the entropy. And their understanding had to do with the super algebra of AdS to
near horizon.
Geometry.
Yes.
Their understanding roughly was the statement that the bosonic part of the super algebra included an SU2. So every supersymmetric state by state, was invariant under this SU2, and that told you that the index was basically the entropy.
I think Benini and collaborators has that kind of explanation in this context. So assume some kind of near horizon AdS2 for these analytic black holes, and they require the superconformal R symmetry the chemical potential for superconformal altimetry of near horizon AdS2, near horizon superconformal quantum mechanics, be 0. I think that's the condition similar to what Ashok did. And then that condition is, yeah.
So I wanted to ask about that. The basic point of one of the things that was powerful about what Ashok and collaborators did was that the R symmetry was non-abelian. So J equals 0 can't move. Here the R symmetry naively is abelian, but is the basic point that the whole superconformal algebra is non-abelian, so it's anyway very tight?
I don't recall the you mean near horizon superconformal.
Yeah, I was saying just if you think of it as a matrix algebra,
No.
there's a path that's bosonic and the path that's fermionic.
Yes, yes.
And the whole matrix is more than a, it's a non-abelian kind of matrix.
Yes, yes.
So I was
yes.
wondering whether that is what might lend tightness to the structure, analogous to the non-abelianness of the SU2.
Yeah, but I was personally very much tempted not to use the near horizon language.
So now that you've got it from the field theory,
yes.
Could I ask Ashok if he has
somehow I also have a similar objection to this Berenice argument that SU2 invariance means that the state has to be SU2 singlet. But U1 invariance does not imply that the state has to be U1 singlet, right? Because you can have charge and charge commutes with itself.
Yeah, sure.
So a charged black hole can be U1 invariant.
Yeah, so but I was wondering whether somehow the fact that the whole superconformal algebra was not abelian, in some vague way, I don't really know.
Could be used. Yeah.
Could be used, yeah.
Yeah, I don't know. It's possible. But one has to do a little more work, I think.
Okay, fine. Okay, I had one more question,
Sure.
if that's okay.
Yeah.
It's a rewording of a question Indranil asked in the talk. If you compute an index, it might appear that you have 4-parameter data about the spectrum.
Yeah.
And actually, when we first started working on the index, this was we thought this was a good thing because there was 4 parameters at a black holes and there's 4-parameter data, so perhaps they could match.
Yeah.
But you explained to us at the beginning of the talk
that
it's likely that there's actually 5-parameter worth of data in entropy of black holes.
From
the hairy stuff.
Yes.
So is it even conceptually possible that this 5-parameter data can be recovered from a 4-parameter index?
I'm not sure. I think this 4-parameter index is just my technical ignorance. I can explain. In some cases, I can do this kind of thing because tomorrow, one of the things I'll do is to study a very, very special corner of the 160 BPS operators called McDonald limit or so on. And in this limit, known black holes are known not to exist. They degenerate down to small black holes. But using this 4-parameter or some degeneration of these 4-parameter indices, I count something new. I mean, I find some new saddle points. So.
But it seems to me that you might get discretely many 4-parameter data. But if there's genuine 5-parameter data, that sounds tough, right? Or not? Am I saying it wrong? Or maybe there's infinite number. Okay.
I think it's tough. I mean, I'm not really sure about even from this is a free energy which has 4 independent parameters. I just blindly superimposed the charge relation to the black holes to that and got the known black holes. But I'm not even sure whether this free energy, depending on 4 parameters, sees known black holes only or something more general. Even that I'm not sure. I'm not sure at the moment,
Yeah, so if one was, sorry.
I'm saying from a point of view of the index, it seems unlikely that you will get 5 independent parameters, right?
Right.
Even in flat space, if you look at the BMPV black hole, for example, it has 2 independent angular momentum.
Yeah.
But the index only allows you to have one of them non-zero.
Right.
Right, and for the black hole, on the black hole side, the other one basically gets fixed. On the microscopic side, you trace over the other one.
Right, but Ashok, there's claimed evidence for actually having a larger set of black holes in gravity. So does your comment make you skeptical about that evidence?
Well, okay. I mean, if we come back to the BMP black hole, there are black holes and black rings.
Yes.
Right, and both I mean, they have different relation with angular momentum. So this may be similar to that. That you can have the index only allows you to have one charge, right? The other one has to be traced. Okay. And it could be that there are different kinds of black holes which contribute to that trace. Okay. Right, but unless you take the trace, you don't define an index, right?
Okay, good. So could I check? So perhaps what you're saying is that this extra fifth parameter set will exist, but you have to. But basically, if you do some saddle point, you will choose the black hole that has the maximum contribution to the index from a real line worth of possibilities.
Exactly. Yeah. Yeah.
Okay. Yeah. So, but that would tell you that then there's still something left to do, because you would want to find the whole real line set of entropies. I mean, if you want to know the question of what is the number of supersymmetric states in a quantum in n equals 4 Yang-Mills as a function of the 5 charges, you've not yet answered the question.
Yeah. So that you can get from the index, right?
Right.
Because the index can only allow you to have 4 charges.
Right. 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 So there's some.
And the solution to that problem is much harder because that's not protected in general, right?
Yeah. Or at least it's less protected.
Yeah.
Right. Right. Okay. Other questions? One last question to both you and Ashok. Should one be able to see that the solution that contributes to the index, so let's say that there is this one parameter line of solutions. Only one of them sort of, at least at large n, saturates, gives you the index. Should one be able to see some property of the gravity solution? Maybe all the other solutions have some extra fermion zero modes or something like that kills. Or you say it's just that they all contribute, but this is the maximum one.
Yeah, I think both possibilities exist. I mean, there could be other extra fermion zero modes, in which case only one will contribute to the index. But if there are no extra fermion zero modes, then both may contribute, but clearly one will be the dominant saddle point, right?
Yeah.
It's very unlikely that it will have the same value at all more than one saddle point.
Sure. Okay. Thank you. Okay, other questions?
Thank you.